Hello and welcome to another video. In this video, we shall see about the modeling of a translational mechanical system. So the basic components of a mechanical systems are spring, damper, and mass. These are the formulas related to a spring, damper, and mass, where F is the force applied and x of t is the distance moved when the force is applied. In case of a spring, the equation is f of t is equal to k into x of t, where k is the spring constant and x of t is the distance moved as a result of application of the force f of t on the spring. In a damper, we apply the force f of t and x of t is the distance that is moved. Fv is the coefficient of viscous friction. The relation between the force applied and the distance moved is given by f of t is equal to Fv, the coefficient of viscous friction, multiplied with the derivative of x of t. Similarly, in case of mass, when a force f of t is applied and the distance moved is x of t, the relation is given by f of t is equal to m into d square x of t by dt square, where m is the mass. In electrical network, we saw that the capacitor and inductor are energy storing elements. Similarly, in the translational mechanical system, we have the spring and the mass as energy storing elements and a viscous damper as the energy dissipating element. In electrical network, we saw resistor as energy dissipating element. So similar to capacitor and inductor, we have spring and mass here. Similar to resistor, we have viscous damper here. We model the mechanical system by using the equations of motion law. Similar to how in electrical network, we used the Kirchhoff's current law, Kirchhoff's voltage law. Here we use equations of motion. We use Newton's law to write the differential equation of motion by summing the forces and setting the sum equal to 0. We will see a simple example here. On the leftmost, we have some fixed position and a spring is attached to that fixed point, and we have a mass and a force is applied on the mass. We also have a damper attached between the fixed point and the mass. So as a resultant of the force applied, the mass is moved to some extent x of t, and that is opposed, that motion of the mass is opposed by this fixed spring damper. So before modeling the mechanical system, we draw the free body diagram. The free body diagram of mass spring damper system is nothing but whatever shows, it is a diagram which shows all the forces that is acting on that mass. So f of t is the applied force and the mass is moved a distance of x of t. Now spring, the force on the spring is k x of t. The force on the damper is Fv dx by dt, and the force on the mass due to the mass itself is m d square x by dt square. And you can notice the arrow mark here. F of t is towards the right, towards the application of the force, and all the three forces kx of t, Fv dx by dt, and m d square x by dt square, all the three forces are towards the left, which opposes the applied force. We use the equations of motion, use the Newton's law to write the differential equations of motion by summing the forces and setting the equal to 0. So here, whatever force is towards the right and whatever force is acting towards the left, both are equivalent. So we just write down all the forces which are acting towards left and which are acting towards right and equate them to get the model of this mechanical system. Since this is a simple system with only one mass element, we have a single equation. Now we will see another example where we have two masses m1 and m2. There is a spring attached between the fixed point and mass 1 with a spring constant k1. There is a damper attached between m1 and m2 with a damping coefficient of f v3. and there is a spring attached between M1 and M2 with a spring constant K2, and there is a spring attached between M2 and fixed point with a spring constant K3. There is also frictional coefficient FV1 with the mass M1 and the floor, and FV2 with the mass 2 and the floor. Sometimes it will be given in the question that it is smooth. At that time, FV1 and FV2 will be 0. Here, in this case, we have the frictional coefficient FV1 and FV2. And the force is applied on mass M1. And due to the force, the M1 will be moving, displaced by X1, and M2 will be displaced by X2. So there are 2 degrees of freedom. 2 simultaneous equations of motion will be required to describe the system. So we have 2 masses. So each mass, by using each mass, we will write an equation. So the first step is to write the free body diagram, which shows all the forces acting on the mass. Here we will start with the free body diagram of M1. So there are forces acting on M1 due to the spring, that is K1, X1, due to the damper, FV1, so FV1 dx1 by dt, due to the mass M1 itself, M1 d square x1 by dt square, due to the damper attached between M1 and M2, FV3, so FV3 dx1 by dt, and due to the spring constant K2, K2x1, and the force F of t. So all the forces acting on M1 is opposing this force F of t. So F of t is only towards the right, and all other forces are towards the left direction. So the force applied, all the other forces will oppose this force applied on mass M1. Now, due to M2, since there is a moment x2 which is related to M2, that is connected through the elements FV3 and K2. So due to that, that will aid the motion of M1. So with all the displacements which is other than the displacement of M1, the displacement of M1 is x1. So all other displacements will aid the motion of M1. So here x2 will aid, whatever force is due to x2 will aid the motion of M1. So here K2 x2 is the force due to the spring with a spring constant K2 that will aid the motion of M1. Also, there is a damping coefficient, damper, that has a damping coefficient of FV3. So damping force is FV3 dx2 by dt. So both the force will be aiding forces. So the force due to the corresponding x2. So with this free body diagram, we will write the equation. So F of t is equal to all the forces that is opposing that F of t. M1 d square x1 by dt square, FV1 plus FV3 dx1 by dt, plus K1 K2 x1. And subtracting the aiding forces, minus K2 x2 minus FV3 dx2 by dt. We'll move on to the second free body diagram corresponding to the mass M2. So the displacement is x2. The displacement corresponding to mass M2 is x2. So due to the spring K2, K2x2, we have a force K2x2 which will oppose the force applied, and FV2 dx2 by dt, FV3 dx2 by dt, M2 d square x2 by dt square, that is due to the mass M2, and due to the spring constant K3, K3x2. And there are 2 forces. These are the opposing forces, and there are 2 forces which aids, which corresponds to the displacement x1. So K1 x1 and FV3 dx1 by dt. So those 2 elements are connected to M2, and that displacement x2 will affect the motion, will aid the motion of M2. So those forces are shown here. Now we will write down all the forces acting on this. There are no applied forces directly on M2, so it is 0. On the left side it is 0. The right side we have K2 plus K3 into x2. fv2 plus fv3 dx2 by dt plus m2 d square x2 by dt square minus fv3 dx1 by dt minus k2 x1. So these two equations will represent the entire system. So that is the model of the system. Now we will see another example. So here we have two masses. That shows that we have 2 degrees of freedom and 2 simultaneous equations of motion will be required to describe the system. Now that is kept on some floor with the frictional coefficient corresponding to each mass as Fv1 and Fv2. There is a spring with spring constant K1 attached between mass M1 and the wall. There is a spring between M1 and M2 which spring constant K2 and a force is applied on M2. The displacement corresponding to mass M1 and M2 are respectively x1 and x2. Now we will start with the free body diagram of M1. We will show all the forces which opposes the motion of M1. So there is a spring attached with a spring constant K1 that has a force K1 x1. There is a damper Fv1 dx1 by dt due to the mass M1 itself, M1 d square x1 by dt square. And due to the spring attached between M1 and M2, we have K2 x1. Now there is some force which is aiding the motion of M1. That is nothing but due to the displacement x2. With this mass M1 is connected to mass M2 using this spring with a spring constant K2. So due to that, we have a displacement. There is a force which aids M1. So we will write all the equations together. K1 x1 plus Fv1 dx1 by dt plus m1 d square x1 by dt square plus K2 x1 minus K2 x2, because K2 x2 is the only force which aids the motion of M1. So it has a negative sign. All the other forces are opposing. So those have positive sign. So here we have for M2, we have the displacement of x2. So due to the spring, we have K2 x2. Due to the damper, we have Fv2 dx2 by dt. And due to the mass itself, we have m2 d square x2 by dt square. And all these are opposing the forces applied due to the f of t. Now K2 x2 is the force that is caused due to the displacement x1 attached using a spring with a spring constant K2. So K2 x1 is aiding the motion of M2. So the final equation will be all the forces that is opposing. So K2 x2 Fv2 dx2 by dt plus m2 d square x2 by dt square minus K2 x1 minus f of t. So these are forces that are aiding, these are forces that are opposing. So these two equations represents the model of this mechanical system. So we will say modeling of few other systems in next videos. Thank you.